recording this today? Okay.
I forgot to record the introductions. I apologize.
Okay, great. Well, welcome everyone. Thanks for participating. I'm not going to talk that much today. I'm going to start with the first slide or two and then turn it over to Jay and Farag, who are going to walk us through it. A little bit of what to expect. Farag's going to give an overview of the, so today is really focused on kind of running the model and looking at how to look at the results, how to analyze the results, how to pull things out of the model. Friday, we'll look more at how do you, if you want to make changes to the model to run scenarios or use the model for your own purposes, how you might go about doing that. So the goal today is hopefully have you guys follow along. I don't know if people have managed to download and install Groundwater Vistas, but if you got that zip file that was sent out kind of late last night, everything should be in there for you to download. And so we've got a few PowerPoint slides, but then we've got some kind of live demos. And the hope is you'll be able to follow along and work through the live demos with us. At the same time, if we do get bogged down, we may have to just keep moving on. And there will be this video that you can refer back to work through it in your own time. So first of all, Farag's going to give an overview of the GSFlow folder structure and the files. Then Jay is going to discuss the surface water output, how to kind of pull out stream flow values at different locations of interest in the model. There's a couple of different ways that that's done. One is through the PRIMS kind of interface, and also one is through the ModFlow interface. So depending what your background is, one may be easier than the other. Then Farag's going to talk about Groundwater Vistas, kind of give an introduction. Hopefully everyone's managed to get it installed. We're running the, I think it's a student version in view mode, so it is free to run for what we need it for. After the break, Farag's then going to actually import the model results and show how you can use Groundwater Vistas to extract them. Then he's going to go through how to what files you need to develop water budgets for the entire watershed, and then discussion of other ModFlow and PRIMS output files. We've got hopefully time for questions, discussion at the end, but as with always, these things, it's best if we kind of have the discussions and questions as we work our way through. So feel free to interject and ask questions. We do have a fairly small group, so hopefully that's manageable. So with that, any questions? Otherwise, I'll turn it over to Farag.
Thanks, Al.
Farag, do you want to share your screen? It's probably easier.
Right. How to do that? Do you know? Like
green button down the lower part of the screen, typically.
Oh, okay, got it. Thank you. Can you see my screen now?
Yes, I can.
Thank you. So I'm going to show the slides here on the left side. You can read along, but I'm going to have a live demo, or I'll show what I'm showing on the slides here for the folder structure. So basically, this is the folder structure that we shared last night. They have some shape files in the GIS folder. We have this executable file to install Groundwater Vistas and an instruction for installing Vistas. But the main GSFlow run are in these two folders for the calibration run and the unimpaired scenario. The folder structure for both calibration unimpaired are the same. Basically, we have the GSFlow executable file and a control file, which is the input file that GSFlow the executable needs. One thing to notice here is this executable file is an updated version from the file that's currently available on USGS website. So throughout the course of this project, we found some things that we brought attention of USGS to, and the SWRCB found some bugs in the code and minor bugs in the code and corrected them, and they sent us a version that that has this correction. So this version is an updated version from the one that's currently available. So to just run the model, we created this batch file. I'm going to open it here. It's a batch file, it's a text file. And this batch file basically has the executable file and the input file that it needs, the control file. And then we'll go through these list of lines later. But what we need to do is double click on this batch file, and it's gonna read and the input files of MSFlow and prems and writes the output files as it goes through. I'm not gonna do that now because the run is gonna take like 15-16 hours to complete, but that's how it goes. Like we double click on the batch file. So the folder structure, we have like a MSFlow folder and a prems folder. That's common in GSFlow, is to have this folder structure. Each of the folder of MSFlow and prems, we have an input and output subfolders, and that will have all the input files for MSFlow. And as the run is going, it's gonna print the output files in here. Because people might need to run the model several times, and every time it's gonna override what's in this folder. We also provided the full solution as we have it for the calibration run in this full solution folder. So we don't, like, if somebody runs the model several times, we still have the files that for the calibration run already in that folder. The prems folder is the same. We have a data file here that has the precipitation and the Tmax, like maximum temperature, minimum temperature for every day within the simulation period from 1993, October 1, 1993 through September 30th of 2017. And there are other input files that prems needs. And then as the run is going through, it's gonna write all the output files in here. Again, we are providing the full solution in that prems folder as well. So if files are overridden, we still have the calibration, the solution of the calibration run. So that's basically the folder structure, the same for unimpaired. The control file, again, is the file that...
Hey, Frog.
Yes.
Sorry to interrupt you. We got a question. Can we slow down a bit?
Sure.
So maybe let's take a beat here to let people ask questions.
Sure.
Especially, I guess, navigating directories on folders. I think people might be getting lost. Does anyone want to? Does anyone have any questions or want Frog to repeat anything?
No, I'll just say that I have all these directories, but Farag was moving through them pretty quick. I was just trying to move up and down and keep up with him, and I wasn't quite keeping up.
Sure.
But it's, I have all the directories. It looks fine. Just slow down just a little. No questions right now.
All right. We'll do. Thanks.
I just want to get a quick. Is anyone that's trying to follow along? Is anyone like falling behind and need Frog to repeat anything? Okay. All right. Thanks, Farag.
Thank you.
Sorry to interrupt you.
No, thanks. The calibration run, we have this executable file. We have the batch file that we double click to run the model. The batch file reads in the control file. And this control file has, if I open it here, I can open it with any, it's a text file. I'm gonna open it with TextPad, but you can open it with any text editor. So here, opening the file, just to look at how the control file looks like. And it has the start time of the model. So we're starting from October 1, 1993. It has the end time of the simulation. We are ending at September 30 of 2017. It also has the name file that's needed by MSFlow component of GSFlow. That's a standard file that's needed by all MSFlow models. That's the data file that we looked at that has the precipitation and maximum and minimum temperatures. This is all PRIMS input files. So the control file has a lot of information, and it will also tell the model where to print the output files for both MSFlow and PRIMS. This is the name file. And the control file also will tell the model what parameters needed, like we need to print, and at what frequency. So do we need to print every month, every year, every day, and what parameters we need to print for PRIMS. For MSFlow, also we have this capability from a file called output control file, which also tells MSFlow what output we need to have and at what frequency. So I'm going to go through these bullets very quick. I went through them already, showing the folder structure, but this is the, again, executable that's received by USGS, and that's updated from the one that's currently available. We have input and output subfolders in each of MSFlow and PRIMS. The control file lists what PRM PRIMS output that needs to be printed and at what frequency. We have the same capability with the output control file on MSFlow. So the two important output files that we are gonna spend some time today discussing them is first the STADVAR file. That's a PRIMS output, which will have stream flows at selected locations. So that throughout daily stream flows at selected locations from October 1, 1993 through September 30 of 2017. So we'll see how we have, like, how this file is formatted in the outputs and how to use it to plot some results. Also, another important output files that we're gonna discuss today is the heads file, and that the file that's what we're gonna import into Groundwater Vistas, and we look how to import it. There's also in the main directory, as the run is going, GSFlow prints daily water budget components for the entire model, and that's the file here. So it's called, I'm calling it here GSFlow Summary full.csv. That's a comma separated file. But once you run the model, it's gonna call just GSFlow Summary.csv. I'm renaming it here because I don't want every time to override this file. And you can, this is a comma separated file. You can open it with any text editor, and also you can open it with Excel. And I'm just gonna open it now. We're gonna also discuss this file today. So that's basically, we have 38 water budget components in that file. So each day we have what is the flow that's coming out of the streams, what is the Hortonian surface runoff to streams, and these are 38 water budget components in each day, and the file is being written as the model is running. But that's a complete file for the whole run. I have also a water budget folder here, which has definition of all these budget variables. So if I open this, this is coming from USGS, and these are the 38 water budget components. That's the name and that's the description. And we can look also at the budget diagrams. So these are the same names that we looked at, and this is just a graphical representation of what these budget components are. We are going to also discuss other MSFlow and PRINCE output files. So in addition to the STAT-var and the heads file and this CSV file, the GSFlow Summary.csv file, which has a budget component for the entire watershed, there are also some useful files that we're gonna discuss today as well. So that's basically the overview of the folder structure of GSFlow. And just if anyone has any questions before we dive into this STAT-var file and how to evaluate or how to look at, visualize, or how to look at the surface water output of GSFlow model run.
We did have a comment in chat when I ran the batch from Randall Hansen. When I ran the batch file before, I also added a command out text after a command after the input line to capture the messages from GSFlow that only appear on the command window. So you may want to do that. Okay, thank you for that. Does anyone have any questions? Feel free to just unmute or use the raise hand feature button in Zoom if you ever, or just type in chat some way of just telling us that you have a question, you want us to pause. But yeah, anything right now?
Yeah, just to elaborate on what Randall said, when you run for those who haven't run a lot of models, when you run the model, it typically outputs a bunch of text and information to the screen that kind of scrolls up as a model runs. So by doing what Randall said there, you can actually save that text to a different file, a text file that you can then look at later, which can be useful.
Thank you.
Great. All right. I think the next step is to look at the surface water outputs. So Jay is going to take over that. Jay, you able to share screens?
Yes. Does everyone see my screen?
Yes.
Yes.
Great. So I will talk about the surface water outputs, and before I do that, I'll give a brief introduction to the Ventura River Watershed GSFlow model stream flow routing network, and then explain how the STAT-var output in the model can be used to extract stream flow time series at specific locations in the model. And later, I'll also explain an alternative option to extract stream flow, which is the ModFlow gauge output. So I'll quickly give an introduction to all of these, and then I'll also do a walkthrough using the GIS files and the model itself. So the model stream routing network in the Ventura River Watershed GSFlow model is this is what it looks like. And the stream network is based on the ModFlow SFR package, the stream flow routing package. And it is composed of multiple segments. And the number of segments depends on which model you're using. So the calibration validation model has 768 segments, and the unimpaired flow model has 786 segments. And each segment, so the segment is just that the stream network is divided into pieces. So each segment has multiple reaches, and each reach is just a model HRU or a stream cell. So a few of these reaches make up a segment, and there are these many number of segments in the model. So just to show you how it looks when you zoom in, so each of these is just a HRU, the model HRU, which is the model cell. And also one of those is also a stream reach, and a few of these make up a stream segment. So I will talk about the shapefile, which is very important if you want to look at the StreamFlow output further also, but just to give a brief introduction, the important fields in the shapefile are the HRU ID, which gives the ID number for each of these cells, and a segment number, a reach number, and the field called outseg, which I will explain later. And the unimp underscore only column tells you if each reach or HRU is only available in the unimpaired model or whether it's also in the regular calibration validation model. And each of these cells, the HRU or the stream reach also has a SFR reach number, which is what is used to extract the stream out time series output. And there are some other information to the right here, like the length of the reach, the stream top elevation, the width, and if there is a rating ID associated with the reach. So this shapefile Farag was showing earlier, there's a folder called _GIS in the main model folder, and that is where you can find this shapefile. So you can open it up in ArcGIS or any other open source GIS software and look at the stream network. So a brief introduction about the StreamFlow output module in GSFlow. So the one that we are using is called StatWar, and it is a statistic variable output module in GSFlow. And this originally comes from the PRIMS piece of the model. So this allows for the output of space separated time series output. And these are some of the control file options that need to be set to output this time series output. And I will actually open up the control file and show this in a bit, but just to introduce the StatWar file option is the name of the file that the output will be written to. The nStatWars is an option to tell how many outputs you want to output, and StatWar names is what tells the model what to output. So for example, here I'm telling that I want the stream flow in CFS for a particular stream reach. And the StatWar element option is what tells the model where to output the stream flow. So if you see here, 1802 is a specific SFR reach number. So I'm asking the model to output stream flow at that location. And to output the StatWar output, you need to have the stats on/off option in the model on, which is set to 1 here. If you set this to 0, then you won't get that output. If you want to refer to any of these in the PRIMS documentation and more information about this, you can look at the PRIMS PRMS 5.1.0 tables, and you will find all the information related to that. So the model already outputs stream flow at certain locations, but what if you wanted to output stream flow at new locations? So you will use the shapefile that I showed earlier, and which I will also open up in GIS and further explain. That is what you will use to locate new SFR reach numbers to add streamflow output at. One important thing which I will explain in detail later is that you need to consider junction reaches because the stream segments can join at junctions, and the flow that you output can vary based on whether you select a reach upstream of the junction, downstream of the junction, or at the junction. And you need to consider that you are outputting the correct stream or catchment that you're interested in. And to output stream flow at a certain location, you need to add the SFR reach number to the StatVar element option in the control file, and also modify other control file parameters as needed. And lastly, this is not needed to output the stream flow, but very recommended is to add comments to the control file indicating what you're outputting through the StatVar output. So comments in the control file start with these two front slashes. So this just tells the model that these are comments and not to look at it, except for just for our reference. So here I have indicated that gate 603A is linked to SFR reach number 1802. So this is probably the most important thing when outputting SFR StatVar output. So the shapefile that I had open earlier, that's the same shapefile here. And this is just a schematic. This does not represent the numbering of stream segments or the link, the network of stream segments in the GSFlow model for Ventura River Watershed, but just a simple example. So you might have one segment. So I've called it segment 500, which is this one. And then you have another segment 300, which is that one. And as I explained earlier, this one, each cell is a reach, SFR reach, and many of these reaches make up a segment. So you have segment 500 here, segment 300 here, and then they're both joining in this junction reach here to form segment 600. So if you're interested in a location to output stream flow, maybe at this location, that one is easy. You will select the SFR reach number, which is related to that cell. So you will look for segment 500 in this column, reach 3 in that column, and then get the SFR reach number from this column. But if the location that you're interested in to output stream flow is maybe located closer to this junction reach, then you will need to consider whether you're interested in the flows coming from this stream or catchment, or the combination of those two. So depending on which one you select, you might get very different answers. For example, if 300 is a much smaller catchment and 500 is a much larger catchment, the flows from here might be much less compared to this one. But if what you're interested is in the sum of flows from this stream segment and this stream segment, then you will need to select 600. So if you select segment 600 and the first reach in that segment, what you're getting in is the sum of flows from 300 and 500, and also any groundwater gains and losses in that particular junction reach. Another thing to note is that there are some specific stream SFR reaches that are not in the shapefile. So I'll open up the shapefile and show in a bit. But if you open the shapefile and check for SFR reach numbers greater than 6632, you will notice that they're all linked to the unimpaired model. So if you open up the control file, you will see that there are some reach numbers that are greater than 6632 in the calibration validation model. And these are stream reaches that are linked to specific diversions, releases, and inflows. So they're only in the calibration validation model and they're not active in the unimpaired flow model. So we have already added flow outputs for these in the control file. So you can look at them in the StatWar output. If you're interested in any of these, for example, the flows in the Coyote spillway or wastewater treatment plant inflows or the flows out of Lake Casitas, if you look in the control file, you will see the number associated with that. And they are already added in the control file, so you can look at it on the output end. When you look at the output from the StatWar option, you will see that it's saved in the prims subfolder output. So I will show it in a little bit, but the original output is just a space separated text file. So you can open it up in any text editor as Parag showed his previous files, or you can also open it in Excel. But there is a custom executable that processes the output. So it takes the header from the text file and the actual output from the text file. So the header is just, it says what variable I'm outputting. So reach_CFS is just the stream flow at a specific reach number. And that's the 1802 is the SFR reach number. And you'll see that there are 820 of those. And the actual output in the text file looks like that. So it's just the ID of the output. So it goes from 1 through the end of the modeling output. That's the year, month, day, and the hour, minute, second, which are 0 because we're running on a daily time step, and all the different outputs. So this number is basically linked to this row. So what this executable does is takes the header, takes the time series output, and just cleans it up and saves it as a CSV file. So since I went through that pretty quickly, I will go through a short demo just to show what it looks like. Change my screen here. Can you see my other screen with the GIS?
Yes, it's come up.
Great. So going back to the model files. So I'll just open the calibration model, but it's very similar in the unimpaired model. So opening the control file again, and you can open this in any text editor. But I'll use one text editor that I have. So if I scroll down, that is the stats on off option that I showed earlier. So if you set this to 0 here, it will not output the statistics, the stream flow output. And this just says what's the name of the file that I want to output to. And NStatWars is the number of outputs that I have, which right now is 820. And this also needs to match the number here, which is what variables that I have that I'm currently outputting. So you'll see that there's 820 of these as I scroll down. And reach CFS is just the stream flow in CFS at a particular SFR reach. And as I scroll down, there's also reach water surface elevation, which is just the water surface elevation at a particular SFR reach. And those are the only 2 that I'm currently outputting. But there are other outputs in the manual if you're interested in those. So I'm just going to scroll down. And anything that starts with these 2 front slashes are comments. So the model does not read any of this. This is just for our reference. So all of this block is just comments. So it goes quite a ways down. And you'll notice that we're already outputting stream flow at pretty fine resolution on the Ventura River at 1/10 of a kilometer, and also on the San Antonio. So if you're interested in any of these and before you want to add a new output, it might be good to look at the control file. We already might be outputting these. The next option here is called stat_var element, and the 820 is the same number that was there earlier. And these are the SFR reach numbers. So there's 820 of these. So as I scroll down, you'll see that there's a lot of these. So those are all the options that need to be edited if you want to either add or remove one of the outputs. So going back to the shapefile, which is in the _GIS folder, that's the shapefile that I'm going to open now. So that's the same shapefile. So just to demonstrate, I have added a few points of interest that I might be interested in. So just examples selected randomly, and I'm going to go to one of them. And opening up the attribute table for this shapefile, this column is the segment number for each of the HRUs, the stream HRUs, and that's the reach number. So you'll see that within segment 1, I have 14 reaches, and each of these reaches is a HRU that has been designated as a stream HRU. And the outside column tells that model that this number 1 segment flows to the number 2 segment. So it can help you understand like which segments are linked to which other segments. And the unimpaired only column, if it's set to false, that means that it's available in both models. If it's set to true, that's only available in the unimpaired flow model. And each of these rows is also, the stream reaches is also linked to an SFR reach number, which is what we'll use to add new statistics variable output. So going to back to the map here, I'm interested in this example location. What I have done is I've turned on the label feature. So I'm showing the segment number, the reach number, and the SFR reach number. So you will see that I have segment 698 coming from here, and then segment 703 coming from here. And just to zoom out a bit, you can see that segment 703 comes from pretty far upstream compared to 698, which is just this short segment here. So depending on what I'm interested in, I have to choose the SFR reach number appropriately. So for this one, assuming that I'm interested in the combination of flows from all of that big catchment here and also that here, I might want to select like the combination of that. So you'll see that this junction reach is essentially the 4th reach of 698, the 17th reach of segment 703, and the 1st reach of segment 706, which is going to the left here. Sorry, my screen's a little bit slow and I'm sharing. So since I want the combination of both of these, I'm going to select the reach associated with 706 here, which is 6109. So I'm just going to write that down, that I'm interested in SFR reach number 6109 here. And going back, I'm just going to turn off the labels for a minute so it's faster. Location 2 And I'm going to turn the labels back on here. This one, you will see that this is sort of a little bit more difficult because I have two of these smaller, well, actually this one's not that small, but this one's pretty small. This small segment here and the larger segment here are joining here at this junction. Anytime you see that a cell has like more than one segment associated, that's a junction. So these two are joining here, and then whatever's coming out of that is joining with whatever's coming from the right here. At this junction ridge. So these two are joining here, and that one is coming in and joining to whatever's joining from here. And right here is essentially the sum of all of that. So in this case, I don't want to include this one. So what I will do is go here, and I just want to capture all of that. So what I'm going to do is select the SFR reach number associated with that cell there. So 391 and 370 are joining to form 405. So I will note down that the number that I'm interested in is 3633. And just zooming out again, I'll turn off the labels for a bit here. So location 3 is again slightly different. I have this stream segment coming here, which is all that catchment, and then another stream segment coming from the right here. So in this case, let's say I'm only interested in capturing what's coming from the north here. So if I zoom in, and look at the numbering again, I'll see that 122 is coming from the north, segment number 122, and then 137 is coming from the right. So if I'm interested in only 122, I can either select this number here, 1018, or I can select this number here, 1019, which is one reach downstream. So I'm going to select 1019, which is just the last reach of segment 122. So now I have three SFR locations, three streamflow locations that I'm interested in that I need to add output for. So if I go back to the model, and I'm just going to open the calibration model, but it's the same thing for the unimpaired model also. So if I open the control file again, and scroll all the way to the top, and I'm going to just search for StatWar. So I'll make sure that my stats on off option is turned on. So that's good. I'm not changing this because the file name is good for me. And I'm adding 3 new outputs. So I'm just going to increase this number to 823. And also increase that number to 823 from 820. And I want to expand this list here because I'm adding 3 new outputs. So what I'm going to do is just scroll to the bottom of that block of text. And I'm going to just say reach_CFS, reach_CFS, reach_CFS. So these are just the new outputs that I'm adding. So 3 new stream flow outputs in cubic feet per second. And the next thing I want to do is if I scroll even further down and come to the stat var element option. Again, this also needs to be increased to 823. All these numbers need to match for it to work. So scrolling to the bottom of that, and I have noted down the 3 SFR reach numbers that I'm interested in. So 6109, 3633, and 1019. So with that, I can run the model. I don't need to do anything else. And I'm just going to make sure that I have increased the number of all of these to 823. So 823. and 823. So the model will run at this point, but just so I know what I have added just now, I'm going to scroll further down again and go to the end of this comments list. And I'm going to start adding a new comment. So I'm just going to call it new outputs. And this can be anything that's following these 2 front slashes is not actually read by the model. So this is just for us. And just call it, I'm just going to give the number that I've added, 6109, location 1. And then I'm going to say 3633, location 2. And 1019, location 3. So we have added the outputs. So if you run the model will, along with what's already there, generate new stream flow output. So assuming that you have run the model, and if you go into the PRMS output folder, the model will generate these 2 files. So this is generated by the model, and this one is generated by the statvar extract executable, which is in this folder here. If you open this file, you will see all the outputs that you added. So I have all the reach CFS outputs at the various SFR reach numbers, and that's just the header. And if I scroll further down, I will see this big block of numbers. So if I'm just going to select 1 day. So you'll see that this is the output for the 1st of October 1993, the first day of the model. And these starting from here is the stream flow output for all the SFR reach numbers that I've selected. And you can also open this in Excel and then split the columns if you wanted to, so that you can have these in separate columns. So just to show what that looks, I'm just going to remove word wrap. So that's just the output. And there's 820 of those. It's a pretty big file. But alternatively, you can go back to this folder and open this processed output. It's the same numbers, just cleaned up and so that it's in a comma separated value CSV file. So if you open that one, all that is the header file, which you've seen earlier, placed on top of the numbers. So that's just the date and the various outputs that you have. So if you've added some duplicate outputs, the model will still run. So if you added 1802 like 3 or 4 times, the model will still run and give you 3 or 4 outputs for that, the same numbers. And the executable will clean that up and remove the duplicates, so you don't have that many outputs for the same location. So you'll see that these are not quite 820. We might have some duplicates, so this has cleaned that up a little bit. That's basically everything regarding the StatWar output. Does anybody have any questions?
Jay, just a comment. We could possibly point out which manuals cover this. Yeah, this is a good introduction, and I think should help people get started. But maybe want to provide some manuals at some point later on following the training.
Yeah, the PRIMS manual, which is mentioned here, has the information about the StatWar outputs, and further in the earlier sections of the PRIMS manual, there's a little bit more description of what this is and how it can be used for. So yeah, we can provide that later too. Does anybody else have any other questions?
Jay, there's a question in chat from Randall Hansen. What tool did you use to develop the SFR model cell shapefile?
Talking about the shapefile.
Yeah.
So we developed that using some ArcPy scripts that were provided by USGS. That's what the tool was that was used to develop that.
And those ArcPy scripts are publicly available.
That's correct.
I think you can download them from a USGS repository, I believe.
That's correct. All it does is it streamlines the GIS processing to create this. But there's other ways of doing that also. You don't have to use that scripts, but it just streamlines it so that you get something that's more in line with the way USGS sets up the model too.
Let us know if that answers your question, if you have more. I did notice that we had a couple of new folks join the audience. There's a 505 area code number and Trey Driscoll. Would you each like to? So you missed we did introductions at the beginning, and we each said name, affiliation, and if you want to provide it, if you have any modeling experience, and the first concert you ever went to. So I'm going to ask if the 505 wants to introduce themselves, and then we'll do Trey Driscoll next.
Hi, wait, am I unmuted?
We can hear you.
Okay, yeah, this is Jim McCord calling in because I was getting bad audio on the computer.
Okay.
Thanks.
Hi, everyone. This is Trey Driscoll with Dudek. I'm a principal hydrogeologist there. I've been working as the project consultant for the Ojai Basin and developed the GSP for Ojai. Very limited practical numerical modeling experiences with actually working with the files, but certainly have used them in a number of basins throughout California. And my first concert was in Philadelphia and was Fish.
Cool. All right, thank you and welcome. Everyone has the permission to unmute themselves, so feel free to interrupt at any time if you have questions. This kind of goes for everyone. So I did want to kind of check in and just see if people people have any questions on the Streamflow routing tool or anything else that's been covered so far. Not seeing anything on mute or in chat. All right, yeah, thank you, Jay. Please continue.
Okay, thanks, Kevin. So I will also briefly go through another way of getting Streamflow out of the model, which is an alternative to the StatWar Streamflow output. So this is through the ModFlow gauge package. And compared to the StatWar output, which you have to give it the SFR reach number, here you have to specify the segment reach number combination. So going back to the shapefile here, StatWar output, you need to give it this number. And for the gauge output, you need to give these two numbers, the segment and the reach. So one thing to note is that the streamflow units output through this method are in feet cube per day, compared to the StatWar output, which has units of CFS or feet cube per second. And to specify new outputs or to look at which outputs are currently being provided, you need to edit the text underscore fixed or GAG, the gauge file in the ModFlow input folder. And the output is saved to the output subfolder underscore ModFlow in each of the calibration, validation, and the unimpaired flow models. You can also edit the .nam file, which Parag mentioned briefly earlier, to change the names of the output files. Another thing to note is that this can also be used to provide.
Hey Jay, just which screen are you sharing? We're seeing the shapefile, the GIS files. Are you looking at?
I'm sorry, I thought I was sharing the presentation. Can you see my other screen now with the slide?
Yeah, PowerPoint file, yeah.
Great. So quickly recap that again. So the gauge streamflow output is an alternative to the StatWar streamflow output. And compared to the StatWar output where you're giving it the SFR reach number, here you have to specify the segment number, reach number combination. So I'll again go back to the previous slide quickly. So StatWar output, you need to give it the SFR reach number, and for the gauge output, you need to give it the segment number and the reach number combination for the locations that you want to output streamflow for. So as I mentioned earlier, the units are feet cube per day when the flow is output this way compared to CFS and through StatWar. So if you want CFS, you'll have to divide it by the number of seconds in the day. And I'll show on the next slide what the gauge file looks like, where you specify output locations. And the output is saved to the output subfolder underscore under ModFlow. And the NAM file is what you need to edit to change the output file names. So the difference, another difference from the StatWar output is that this file can also be used to provide model output such as stage, volume, and evaporation, etc. for Lake Casitas and Matilda Lake, and also diversion flows for the Robles diversion. Just to note, these are not active in the unimpaired flow model, so these are only in the calibration validation model. So to quickly show what the various files I mentioned earlier look like. So the gauge file in the ModFlow input folder looks like that. So I'm telling the model I want output at segment number 210 and reach 2. I'm just giving it a unique ID called 101. So there are notes here to indicate what these mean. So segment number, reach number, unit number, which is just a unique ID. And the 4 is just a ModFlow specifier to give a certain kind of output. So that doesn't necessarily have to be changed. It just adding 4 will tell it to output multiple output types to that file. The NAM file is what tells the model like what the output file name should be. So I'm telling it for 101, which is 603A. I want that file name. So gauge01 underscore 603A.dat. So those are just the various output file names. And these are just the model outputs, the same list that you see here. This is what it outputs when you run the model. And if you open one of these, this is what it looks like. So the header just tells you, and this is output for segment 210, reach number 2, and this is the time series output. So you'll notice that this is just the model number of days. So one is October 1st, 1993, and it goes all the way to 8766, which is the last day of the model run, which is September 30th, 2017. And this is just the stage at that location, the flow in feet cube per day in that location, and various other outputs at that location. That's,
Can I interrupt with a question?
yes.
We have a question from Randall Hansen about the StreamFlow routing tool that was discussed earlier. Randall asks, would you please give me the reference and URL for the SFR tool you used for developing the GIS model cell shapefile, please? I'm not aware of that being publicly available, but like to see what you got as we had one at the USGS, but it was not publicly available. Thanks.
Yes, I can add that.
Okay.
And Jay, is that a GitHub repository or something?
It is a GitHub repository. Yes.
Yeah, and I think there was a paper published too, right, related to that.
That is correct. Yeah.
Yeah, I'm looking to see if it's referenced.
5 years ago. Yeah. So
I'm
we can post that maybe over the lunch break. We can dig those up or something.
Okay.
Thank you all.
Yeah. Does anybody have any other questions?
Great. Thanks, Jay.
Yeah, thank you.
Next up, I think we're going to switch to a Groundwater Vistas introduction. I'm wondering if we need a little break before that.
Sure.
I don't know, 5 or 10 minute or something, and Farad can take it away. Does that sound good to everyone?
Before the break, just want to make sure that everyone has the chance to download Groundwater Vistas. And if not, we can use this time of break to download it.
Okay. Yeah. So if you haven't downloaded Groundwater Vistas yet, please do so. That's in the zip file that was sent around to all the participants, right?
Right.
Okay.
Yeah. So running the executable will install it, I guess.
Yeah. So that should be in the zip file that Al sent around yesterday to all the participants. If you haven't installed that yet, please go ahead and do so. If you need help with that, let us know. Otherwise, let's take a 5-minute break, and then we'll come back and we'll see if anyone needs help with that installation.
I'm just adding to the chat the link that Randall was asking for. It's also referenced in our model documentation report.
Thank you.
We're back at 11:25.
Yeah. Well, and that'll be a slow comeback just to help people that are having problems. So I see Brian has a problem. Okay, so we'll start working on it in 5 minutes with you, Brian. All right, folks, welcome back. If we have a few minutes, I think it would be helpful to try and help anyone that's having errors installing groundwater vistas. Brian Epstein posted an error in chat a few minutes ago. This is something that Greg or Frog you're familiar with. And Brian, feel free to unmute and talk to us.
No, I'm not familiar with this error. Don't know if it's related to like system requirements on the computer to download vistas. But DLL files usually are system files. So Brian, did like were you able to like unzip these files and install them? Like when did this error came?
He might not be back yet. Brian, let us know when you're back. We'll try and help you with this error that you have. Okay, welcome back.
So hi Brian, I was asking like when did you encounter this error? Like did you unzip these files and install them?
Yeah. Let me get rid of this chat that's in the way. Hold on. Yeah, let me run through that again real quick. Hold on.
So first you'll need to unzip these files and install the vistas first, and then install this one. And then you'll be able to open hopefully the files that's in the MSFlow Groundwater Vistas folder.
Okay, let me run through and do that.
Okay.
Are there any other questions from folks on installing groundwater vistas?
Should I proceed?
Yeah, it sounds like we haven't heard any other requests for help, so
yeah,
please continue.
So just emphasize here, this is like one way of many ways to visualize MSFlow results. Everyone might have, someone might have a different tool, and there are many publicly available tools as well. So the vistas files, the executable files, or the zip file that I have here on the Groundwater Vistas installation, we are distributing them, but they can be downloaded from the ESI, Environmental Simulation Incorporated, at groundwatermodels.com. And we have also installation groundwater, like a step by step on how to install and how to open groundwater vistas. So all of this is provided. So hopefully everyone is able now to install it. And I'm gonna go minimize this presentation and go in a live demo. So what's happening when I try to open vistas, I'm gonna open it also with the student version, which is the free version that's available, but you can only view results. You cannot run the model in vistas. You cannot change things and run the model. You can only import results, export results. It's a view mode only. So I'm gonna open the file in the student version in the view mode only. So it's gonna be similar to everyone else. So when I open it, I will have this message, model is too large for the student version, and it's opening in view mode only. So I hit OK. And then it will ask me about the directory where I will have my results. So I'm gonna choose directory now. So I'm gonna choose, like normally I have the results here in the ModFlow output directory, but I'm having the complete results in the full solution. Just as I talked this morning, that because we don't want to overwrite the results every time, I have the complete results here. So I'm gonna choose this folder, the full solution. So it asks me about a series of map files. The model we can work with the model without these map files. It's just a way to orient the user to where the model grid is. So I have a series of map files here, and it will ask me about where the map files are. So I'm having them at this folder, the maps folder. So I'm gonna choose K, and it's gonna ask me about 5 map files. So every time it's in the same folder. So that question is gonna be repeated 5 times. So now I'm able to open vistas. The map files here are, for example, the groundwater basins. So we know that relation of the model grid to real world coordinates this way. It's not needed by the model, just orient the user where the model is and where the grid is. So I'm gonna spend the next 15-20 minutes just making everyone comfortable with groundwater vistas. A lot of people I know that have a great experience with vistas, so sorry if it's gonna be a redundant information for you. First thing, I can remove this finite difference grid to make things easy to see. So I go to plot to display, and then I have a check here on finite difference grid. So I'm gonna uncheck it. So now I uncheck the finite difference grids. I can have zoom into a certain portion of the model by clicking on this W. And then I can zoom in a certain portion of the model. So I can go back to showing the full grids by selecting this option, view full grid. So I'm hoping everyone can follow along with these, but we have the recording, and if someone wants me to slow down, I'm happy to do so.
Any questions so far from the audience? Is Frog going too fast? I don't see anything yet.
Yeah. So I can choose different layers of the model. So we are now in layer 1. I can choose layer 2, layer 3, and layer 1, 2, 3 are active through the entire watershed. The gray area here is inactive cells. Layer 4 is going to be active only in the deeper portion of Ojai Basin. So that's the extent of layer 4 in the model. And I can go layer 5. It's even smaller footprint, and it's like a ball shape, and layer 6 and layer 7. So these are the extent of each model layer in the model. There are, I can see boundary conditions. This is edit boundary conditions. This is edit property zones, and that is analytic elements. Analytic elements is what we see here as blue circles, and that's basically wells in the model. So I'm going to go through these 3 manuals here. So these are the analytic elements, which are the wells simulated in the model. Again, I'm going to show the foreground. So this is the boundary condition from the drop-down menu. There are many boundary conditions that I can select: the constant head boundary, a general head boundary, stream boundary. All of this can be selected. Also, from the property zone, I can select multiple different property zones like hydraulic conductivity, storage, top elevation, bottom elevation, initial heads. So whatever I want to visualize, I have to select it first. So if I want to visualize a constant head boundary, so I have to select first this option, and it's already on the constant head boundary. I know that the constant head boundary is simulated at the lower Ventura, just represent the ocean there. So I'm gonna zoom in this area. And these are the cells for the constant head boundary. If I move the cursor to any of the cells, you can look at the numbers that shows here. So this cell has a head of 2.5 feet, and this cell also has a head of 2.5. And I can select any of these cells by double-clicking on it. And it will give me the row number, the column number, the head of the boundary, and it's constant there. Also, I can show the transient data. And we have 288 stress periods in the model that represents each stress period is a month. So we have 288 months from October 1993 through September of 2017. And that's the head in each of the stress periods. So we have a constant value in all stress periods of 2.5 feet. I can move to layer 2, and that's also, you can see here the head, 2.5 feet in all these cells. I'll show full grid again. I know that we are simulating a general head boundary here for the upper Ojai Basin at the boundary of the watershed. And if I zoom in this area, so the cyan color here is what represents the general head boundary, and I can see that head here is 1520, 1525. I can look at the different head values in layer 2. If I double click on this one, it's not going to do anything now because I'm not selecting that I want to see general head boundary. So to make it work, I have to select a general head and double click on this, and it shows. So row number, column number, that's the head of the boundary, that's the conductance at that particular cell. If I show a transient data, I have the same head in all 288 stress periods and the same conductance as well. I can go to layer 3. That's basically a bedrock here. And if I double click, I would see that a smaller conductance because we have a smaller hydraulic conductivity in the bedrock. I'm going to show the streams. I'm going to show the grid again. Go back to layer 1. And of course, all of this are the stream network that Jay showed. And we had a shapefile for this. If we move the cursor to any of these, it will say here, we'll say, for example, this is stream 152 reach 7. Let me zoom in this area. So that is stream 104 reach 20. Again, if I'm gonna double click on it, it won't show anything because I'm not selecting streams here. I have to select streams here first, and then double click. It tells me the segment number, the reach number, the stream bed elevation of the stream, the hydraulic conductivity of the stream beds, manning coefficient, the slope of the stream segments. So all of this information is already, we can visualize that in vistas. This is, I believe, it's going to be a junction shell, a junction stream reach, because it's combining multiple streams. So I'm going to double click on this one. So this one has segment 104 reach 21. This one maybe. So this is segment 1448 reach 6. But yeah, some of these cells are going to show multiple times. That's the same one. Yeah, so here, for example, this cell, the same row, the same column, and we have a junction cell here. And if I click on it, each time it will tell me this is the bed elevation, that's the segment number, reach number, that's another segment number, another reach number at the same cell because it's a junction cell. And that's also a segment and the reach number. That's probably the combination of both segments because it starts with reach number 1 here. So that's for the boundaries. We can select different boundaries and look at them same way. We can, for example, look at the lakes here. We have 2 lakes. This is Lake Casitas and this is Matilha Lake. But I'm gonna go to hydraulic or property zones and try to visualize that. So I'm gonna select, instead of boundary, edit boundary conditions, I'm gonna select the hydraulic conductivity or property zone. Now I'm selecting hydraulic conductivity. So again, everything shows here. So that's zone 27, and it has a horizontal hydraulic conductivity of 0.01 feet per day and the vertical hydraulic conductivity of 0.001 feet per day. That's another zone number, different hydraulic conductivity, horizontal and vertical. So each color of these is a zone that has its unique horizontal and vertical hydraulic conductivity. So we can move the cursor and look at the different zone and log the associated hydraulic conductivity in the different zones. We can move to layer 2 and do the same thing for layer 2, layer 3, and so on. What it shows here, these channels, these are alluvium channels. So if I'm going to zoom in and select one of these light colors here, that's alluvium here, and I have a high hydraulic conductivity along the alluvium along the streams. So I have a hydraulic conductivity, horizontal hydraulic conductivity of 5 feet per day and the vertical hydraulic conductivity of 0.5 feet per day. So again, you can move the cursor and look at the zones and the hydraulic conductivity associated with the zones. Another way is to go to properties, property values, and database, and just see the different colors. So that's, for example, that's zone 3, and it has this hydraulic conductivity 150 feet per day and the vertical of 15. So that's zone 3 here. So that should have 31 zones in there. I have 32 because 32 I'm assigning to all inactive area in the model. So it has a 0 there. That's not part of the model. But we have 31 active zones. And that's the extent and the hydraulic properties of each zone. I can also select the storage properties. So these are the exact same zones as the hydraulic conductivity, but you can, like, now we're showing the storage coefficient. So that has a specific storage of 10 to the power -7, a specific yield of 0.001. And along the alluvium, we of course will have a higher specific yield. So here in this zone, we have a specific yield of 0.03. Again, we can look also at the table, the database table there. So we have the same zones, the same colors, but it now shows the specific storage and the specific yield for each of the 31 zones, and 32 just the inactive area of the model. We can visualize, can visualize also top elevation. So each cell now, look here, each cell, that's the elevation of top of layer 1. That's top of layer 2. We can select bottom elevation. So bottom layer 1 is going to be top of layer 2, and bottom of layer 2 is going to be top of layer 3. So layers goes from layer 1 at the top to layer 7 at the bottom. And another way is to look at the cross section here in vistas. So we can just maximize this window. I can make this go throughout the whole width of my screen by selecting, maybe I want to select, zoom into this area here. And that's the cross section. So that's the cross section associated with row 117. I can choose different row and look at how the cross section moves at different rows. So that's a row here. And I can also choose a column and look at the cross section this way. I'm gonna minimize that. Another way is to look at the analytic elements. And that's what we're going to spend half of the afternoon session. And the analytic elements are these wells here. So I can zoom in, select this analytic element. To select it, I have to activate this and edit analytic element first, and then I'd be able to select any of these elements by double clicking on it. So by double clicking on this, tells me the well name. It goes from layer 1 to layer 5, and that's the bottom elevation of the well. So if that simulated water table falls below this elevation, then pumping is shut off. That's going to be dependent on the well depth. And I can also see the pumping, the time series pumping by clicking on the transient data. So these pumping are negative, meaning it's out of the groundwater. So it's a pumping, not injection. And just the pumping here in cubic feet per day. So in the first month, in October 1993, for that well, I have that amount of pumping simulated. In November 1993, I have that amount of pumping. So in the first training on Monday, Al and Greg went through how we came up with these pumping information, either it's known information or from supply and demand analysis. So we can either go and select a well and look at the well name and look at the transient data. Here we are starting from 106, which is like 10 years or 9 years after the start of the model. So that probably this well was not drilled in 1993. It was drilled sometime in the early 2000s, and that's why it was not part of the model at the early stress periods. Another way to look at the analytic elements here is to go to Edit, Analytic Element List, and just we have the types here. We have two types of analytic element, either targets or wells. I'm going to go to wells. So if you have a specific well name that you want to look at, instead of going and eyeballing where the well is and double click on it, you can go to Edit, Analytic Element List, and choose the well that you are interested in, and it will give you the information for that well. And we can look at also at the transient data or time series pumping for that well. So any questions so far?
Does anyone have any questions for Farag? Are folks able to follow along, or do we need to go back over anything? Okay. Please continue.
So I think that's it for now. I like my next thing is how to import and export results in the model. But I think that's a good way to stop here and leave that early for the afternoon session.
Okay. So yeah, like Rog said, we'll stop here for lunch. Maybe we'll stick around till noon if people have questions or anything they want to ask about. And we'll resume at 1 p.m. But does anyone have any questions? Are you able to follow along?
Ryan, were you able to get it installed?
Brian, if you were trying to talk, at least I couldn't hear you.
Oh yeah, it turns out if your microphone's up by your hairline, it doesn't really work real well. I'm getting the same error with the code execution cannot proceed because MFC 140.dl was not found. reinstalling the program may fix this problem. So I was saying, I'm not sure. I'm running Windows on parallel on my Mac, so I'm not sure if that's the problem, and it's not putting the files in the right location, and or is looking in the wrong location for the files, or what exactly is going on. But
Yeah, I'm not sure the system requirements, but if you go to the website here, groundwatermalls.com, it will tell you the system requirements for vistas, groundwater vistas.
I'll have a look over there. Thanks.
Is there also any questions? Otherwise, we'll break for lunch and return at 1 p.m. Not hearing anything. Okay. I'm gonna pause the recording and hope everyone goes and enjoys a good lunch, and we will be back in 1 hour.
Thank you.
Great. Thanks, everyone.
Okay, we are back again. Hope everyone enjoyed their lunch. Were there any questions that people thought of during their lunch break? And as a reminder, all the participants should be able to unmute and chat with us, or type in chat if you want to. Not hearing anything yet, so guess we can continue. Please continue.
Great, thanks, Kevin. So Farag, you're gonna, just to recap what we're doing, we're gonna look at the groundwater vistas, importing and exporting results, and then some water budgets, how to calculate them, and then some other output files. So Farag, take it away. I think you're on mute, Farag.
So this is groundwater vistas. We looked at updating or looking at boundary conditions and hydraulic properties, conductivity and storage, top and bottom elevation. Now we want to import groundwater heads and look at the contours. So to do so, we have to import, go to plot, import results, and it will ask about the stress period and the time step I'm interested in. So we have 288 stress period. Stress period number 288 is for September 2017, and time step 30, meaning that September 30 of 2017. If I hit browse here, it will show a list of stress periods and time steps where I can export, I can import results. We're like printing results at the end of each month. So that's stress period 1, that's October 1993. Time step 31, that's the end of the month, and we can see like there's 288 stress periods, and that's September of 2017. So I'm going to select this one, which was the default there. It's going to take a minute or so to import groundwater contours. So basically, it's reading now the heads file, which is a binary file. It's unformatted, so it's not a text file. You cannot open it with text pads or any like text editor. You have to have a special program to visualize this. And Vistas is one of these programs, but it's not the only tool. So now it imported the results of September 27, and it draws the contours here. I think I'm having the contours every 100 feet. I can go plot contours, parameters. So I'm plotting the contours every 100 feet, but I can change that here. If I move the cursor to any of the cells, you can see that the head value is going to be printed or is going to be shown here. So here I'm an inactive cell, so I don't have any head results. It's -999. That's the default for inactive. But if I'm going to move inside the model domain, I have different heads. So here at the mountain, I have 3,800 feet, that the simulated head at this location as of September 2017. If I move the cursor now inside the basin, inside Ohio, I have like 750, 760. If I go to lower Ventura, like 145, something, then near the ocean, of course, I'm closer to 0 or 2.5, which is the constant head. I'm assigning at the constant head cells here. So that's layer 1. I can look at layer 2. Again, these are the contours in layer 2. Can look at the head value here. Okay. Layer 3. Mostly this is a bedrock layer, except for an Ohio basin. And layer 4, that's the deeper portion of Ohio. I can select another month by going to plot, import results, and if I hit browse again, I select any month, and then when I hit OK, it's gonna upload here and draws the contours associated with this month. So any questions so far? So now, if I want to export the results, I have different tools, or like I have one tool to do that, but there are different ways. And you remember when we looked at the analytic element list, by going here and then go to edit, analytic element list, we can see 2 types of analytic elements. One of them was wells, which we went through before lunch, and these are pumping wells. We can double click on any of these, and it will show the pumping rates assigned to this well for the simulation. And then there are targets, and targets are the location in which I'm interested to let the model export heads at these locations. So in addition to visualizing the contours, I may be interested in plotting time series simulated head at a certain location. So that's what the targets are. And I can, like, could be interest to simulate or export the results as a time series for all the months in the model, like end of each month. So I will have 288 values for the target. Or I can have, if I want to have simulated head at specific dates. Like potentially these are the dates where we actually have measurements. So we might have a measurement in October 16 of 2004. And I know the measurements in this location at this day, and I want the model to export the results at the specific location and the specific day. And so I can see that's how I designed this, as having 2 types of target names. One that starts with mon and then the stateful number. And these are the targets. Let's say I'm interested in exporting results as a time series for all 288 months, regardless if I have data or measured data at these dates or not. Another target name is start with targ and then the stateful number name. And these are the targets where I have actual measurements at specific days, specific dates, and I want the model to export the results at those specific dates. So if I hit on like any of these, maybe I'll select the first one, 3N23 W5 V1S, and this is the target name. Remember that these are the targets that I want to have export results at the end of each month. So I have a time here, 31. So that's the time in days since the start of the simulation, which is September 30th, October 1, 1993. So time 31 is like end of October of 1993. Time 61 is the end of the second month and so on. So you can see that I will have 288 times here. That's the end of each of the 288 months I am simulating. I don't have any target value because I'm selecting, I want to plot the simulated head at all these dates, regardless of I have a measurement at this day or not. So if I select any of the mon targets, it's gonna be the same thing, just all the times and just a dummy number for the target value. So if I go to targ and I select any of these and go to transient data, these are actual dates I have and the actual measured values in feet for that day. So time 32, that's like November 1 of 1993, because I know that time 31 was the end of October and 32 is November 1 of 1993. So for this well, we had a measurement in November 1 of 1993 of 258.5 feet. At day 365, that's sometime in September of 1994, like a year later, we have a measurement of measured head of 245. So I have the actual time here in days and the actual measured values. So these are the two types of targets. And if I go to plot, I'm sorry, if I go to the reports, calibration, and then target residuals, we'll say, well, is that the location you want to have the targets at or the output at? So I'm having output full solution target report. It's a CSV file, the comma separated file. So I will hit OK. Everything now is set up by default to hit OK on that. So it says report created successfully, and I can look at here, or I can open the file, go to MSFlow, output, full solution. This is the file that I just created. It has 1:12 p.m. that just the day. So I'm gonna open this, can open it with Excel, and it will have this information. So it has the name of the target, the XY location, the row, column, layer, group, zone, time and observed value, computed value, and the residual. So this is first, all of these are start with torque. These are the ones where I have measurements at selected dates, and these are the days. So I don't know what this day is. It's somewhere like 20 years, not 15 years, 20 years, something like that after the start of the simulation. That's the observed number. That's where we have actual measurements at this day, and that's what the simulation tells us about this day at this location. So this is just, all of this is just one well at different times, and that's the residual between the computed and the observed. This is another well here. Again, I have the times, so I can have something like that. So I have a well and the times and the observed and the computed value. If I scroll down and go to the MON targets, these are all targets where I have the actual times. But if I start to go to the MON, times starting from here, then you'll see that the times are now end of each month, 31, 6, that's October 1993, November 1993, December 1993. I don't have any observation, that's just a dummy number here. But of course, we have the simulated values at these dates. Of course, the residual here is like, we don't worry about because we started with dummy numbers for observed values. So I can have this targets from here all the way up to evaluate the calibration by looking at observed versus computed. Starting from here all the way down, I can have for each well, I can plot these numbers as a hydrograph for that specific well. So these are, well, I have 288 of these, and then I have another well here. Should be to another 288, same times, and just different computed values. Any questions so far?
Just as a reminder for everyone, especially those that have joined recently, you all have permission to unmute if you want to talk to us.
Okay, so I have, I'm including also a spreadsheet. I think it's here. Oh, probably didn't include that in here, but no, it's here. So under Groundwater Vistas, so this is the CSV file for the targets that I just created. I'm gonna open it again. That's how it looks like. I'm gonna copy everything. And paste it in this file here at the calibration targets. So when I do that, everything now is using formula to have the calibration statistics, a figure like this, and this figure is calculated using the targets. So where I have measured at actual dates, and now the model is calculating the simulated at these specific days. So I can use these targets when I plot everything in here. This file used this targets to plot a scatter plot like this. But also the file here has the mon target where I have times and observed, which is a dummy value and just computed. And the model also plots hydrographs for all these mon targets, and it shows here. So that's the blue line here. So that's the simulated. So this blue line has 288 points in it. That's the simulated values at each of it at the end of each month. So that's for Lower Ventura. That's for Upper Ventura. That's in Ohio. It's in Upper Ohio and outside the basin. And that's also for Metelha and Casitas lakes. So it's a very straightforward, just go to reports, calibration, target residuals. Okay, it's gonna create that file here, the target report.csv file. Anyone can use this file knowing that it has information for targets, different types of targets. And then the spreadsheet is just a tool if someone wants to copy that into the spreadsheet and look at the results this way. But there are different ways to visualize the results in that CSV file that's created. Any questions?
Does anyone have any questions so far? Oh, we have someone unmuted. Go ahead.
Yeah, I have a question. This is Steve Stewart. Have you posted, say, the residual circles or bubbles on the map just to see where spatially your error is occurring? That's something you can show us how you would do it here?
Because the residuals can be we can plot the average residual, because if I look at the residual here, so this is all one well, and I have residuals that's going from -1 to -6. This is another well that has different residuals, some negative, some positive. Probably the mean error is going to be somewhere closer to 0. But yeah, I don't remember. I plotted personally. I calculated the average residual for each well, but I didn't do that personally, as to plot the average residual on a map.
Okay.
But all the information is here in this target listing. And also but that's not a spatial distribution. That's just, and here we have, looking at this residuals graphically with the scatter plot. And this is just a statistics for residual. So that's the R, which is the goodness of fit. So it's between 0.92, 0.93 on the high to 0.99 overall. And the high is these green dots here. So we understand that there could be also interest in people adding other target locations, and exporting the results, or looking at the results at these target locations. Maybe if the simulation is like continued in time, probably add more water levels to existing targets. So we provided a tool to create this target file. And that's here in the create target file. So we have this executable file that first I'm going to look at the information that goes into this executable file. So I have this spreadsheet. So the spreadsheet reads two input files. One is location, well name and location of wells, layer, and the group. And the group is just, I'm having that as either Lower Ventura, Upper Ventura. So Lower Ventura is 1, Upper Ventura is 2, Ojai is 3, Upper Ojai is 4, outside the basin, groundwater basin is 5. So I have 5 groups. So if there's an interest in calculating the statistics by group or something. So I have 60 wells. In addition, I'm adding 2 for Matilha Lake and Lake Casitas. So I have 62 total here. So I'm having the well name, the X, Y, layer, and the group. So that's one file. The other file is a master water level. So I have the well name, the day, and the water level. And the day, that's the date, November 1st of 1993. And then calculating the day, just a formula of subtracting September 30th, 1993 from that day, that date. So here I have December 2nd, which is day 63. It's just almost subtracting September 30. So this is February 9, which is day 1593. So I can copy this, which has the well name, the day, the water level, and the depth, and copy it into another text file. So I can work on this spreadsheet, add more calibration targets, or add more water level measurements to existing targets. And then I will copy these 2 spreadsheets here into these 2 text files. So the first text file has the well name, the XY, the layer, and the group. And I have 62 of these. And the second, just the second tab in the spreadsheet has the well name, day, and this day is the date, actual date minus or day since the beginning of the model, basically. And that's the water level. So when I have these 2 files, I can double click on this target executable file, or I also have this as a batch file. So I can just double click on this batch file, and it told me like it continued And you can see that import targets now is created. It has just this day. So this file is just created, like use this executable file along with these two input files and create this import targets. And that's a text file. If I open it, so it creates the information in these two input files in a certain format that can be imported into Vistas. So it has the well name, the XY location, that's the layer, that's the group number, either 1 through 5, which is location of this target. This is a weight for now. We're having a weight of 1 in all targets, and that's the number of measurements for that target. So we have 11 measurements, and these are the 11 measurements we have. That's the day, and that's the measured water level. So this well, we have 12 measurements, and these are the 12 measurements. Here we have 21 measurements, and all of these are target wells. These are the targets where we have actual measurements at specific days. So if I scroll down here, this also creates this MON targets. So I will always have 288 because that's like end of each month. And this is just a dummy number here of -999. So I can recap, I can change values here, like add calibration targets in here, add water levels in here, copy these two tabs into these two text file, run the batch file, it will create an import targets to that file. And then I can import that in here. Any questions so far? So to import the targets, I need first to delete all the targets so I don't have duplicates of the targets. So I go to edit, select all targets, and say, are you sure you want to select all these targets? Yes. And then I'm gonna hit delete on my keyboard. So now I delete all the targets. If I go to edit, analytic element list, I will not see any targets, all wells there. So I assume that I already created a targets where it has more wells or more water levels, and I just went through the process and created through the batch file and created the import targets. I want to import that target file in here. So I go to plot. I'm sorry, I go to analytic elements, import target text file. And to ask me about the location of the target text file, I go, I think it's MSFlow, outer vistas, let's say create targets. I know it's a that file. You can see this is the file that we just created 4 or 5 minutes ago. That's import targets. So I'm going to select that file. I want to import that. So now I need to let the model know which number is in which column. So I'm gonna look here at the view file. This is the file we just looked at. I know that I have the target name is in column 1, the XY are in column 2 and 3. This is the layer, column 4. This is the group 5. The weight is 6, and then the number of measurements is in column 7. So I have 7 columns there, just to remind myself. But should have this already by default. So column 1, the name, 2 and 3 are the XY coordinates, 4 is the layer, 5 is the weight. Probably I said that I switched between the weight and group. 5 is the weight, 6 is the group number, and 7 is the number of transient data points that I have. Double check, like check on these. The targets are inside coordinates, and I have transient targets. So each target has different times and different water levels. Just not just one water level at one date. It's multiple. So I need to check these 2 boxes here. And these are the columns as this tool creates the targets. If I hit OK, it's gonna import 122 targets there. Make sure that it's correctly imported. So I go to Edit, Analytic Element List. I can see the targets now, and it has both the MON targets, 288 times, just a dummy value for the measured water level, and targets, and here actual dates and actual measured water levels. So Jay in the morning went through the process of how to look at the stream flows 2 different ways, the STADWAR file or the gauge file. Here is just how to visualize groundwater heads. And export the results of plots, scatter plots, and hydrographs for monitoring wells. Any questions?
Does anyone have any questions right now? People, are folks falling behind or able to keep up?
So that's the end of the groundwater vistas. Next, I'm gonna talk about the budget of how to visualize or not visualize, how to just see the budget information and water budget calculations. But that's the end of my live demo on groundwater vistas.
Thank you, Farag. Any questions on groundwater vistas before we move on?
Okay. Should I proceed?
Yes, please. I haven't seen anything.
Okay. So this was a live demo and importing and exporting groundwater model results. We're done with that. I'm gonna go to slideshow here. So now I'm gonna talk about developing water budget for the entire watershed. Do you remember early in the morning, we looked at some budget diagrams, the figures from USGS, and we looked at that file called GSFlow Summary.csv, and that has lists of 38 daily water budget components that cover most components of the full water budget. And there is a text file that explains each of these components, but there's also a graphical visualization of what these components are. So it's like precipitation, that's precipitation that goes into the soil zone and in the stream and lakes. So we have the soil zone, that's this area here. We have the unsaturated zone. We have the saturated zone. And then we have lakes and streams. And this is the land processes. So that's where the precipitation falls in, and we have Hortonian surface runoff to streams and Hortonian surface runoff to lakes. This is all part of the land processes. And after that, we have also evaporation from impervious areas, and there's fall through, that's infiltration to the soil. And then we have the cap ET, that's evaporation from the soil, change in storage in soil. And then we have this drainage, soil drainage from the soil to unsaturated zone. We also have this component, which when the water table is high enough, it discharges back into the soil zone. And that's called sat to graph Q, or in MSFlow, it's called surface leakage. We have the pumping here. That's the net well flow Q. That's the pumping from the saturated zone. We have exchange between the saturated zone and the lakes and streams. We have boundary stream flow Q. That's like any inflows that goes to the stream, like the wastewater treatment plants. That's gonna fall in here at this budget component. That's stream out Q. That's any water that's leaving the model through the stream network, like diversion or water through to the ocean.
Hey, Farag, this is Trey Driscoll with Dudek. Can you confirm the time steps for the groundwater surface water interactions in the model?
Right, that's a good question. Thanks, Trevor. So we have a monthly stress period in MSFlow, but we have daily time step for the soil zone. And what happens is the soil calculates everything on a daily basis and passes these flows into MSFlow on a daily basis, and it gets into the calculation on daily basis as well. So for example, the pumping, we are defining it every month, and it's distributed uniformly throughout all days throughout the month. But this component here, the soil flows from the soil to the unsaturated zone, that's computed and used daily by MSFlow. Also, the exchange between streams and the saturated zone, that's also computed like daily within MSFlow. So we have daily time steps, and recharge exchange is computed daily.
So that's an important difference between GSFlow and MSFlow, that you have daily time steps throughout the entire period. And that's one reason why the model takes 16 hours to run.
Thanks, Greg.
Sure.
Any other questions? As I mentioned, these 38, if we count these between inflows and outflows and change in storage, these are 38 water budget components. But I'm saying it covers most components of the water budget, because we noticed that there are some components that are not reported in that file. They are being calculated correctly, applied correctly in the model, used correctly in the equations, it's just not reported in that file. And we noticed that when we, for example, looked at the mass balance for the soil zone. So that's this area here. So not all these budget components are going to be used when we look at a certain area in the model. So if we look at the soil zone, for example, these are the only components that are in play. These are the inflows, outflows, and change in storage. Inflows to the soil zone, outflows from the soil zone, and change in storage in the soil zone. So we have the fall through from the land surface to the soil zone, that's inflow. We also have the surface leakage. If the water table is high, it discharges back into the soil zone. That's additional inflow to the soil zone. We have outflow from the soil zone. This is the evapotranspiration from the soil zone. And we also have recharge from the soil zone to the unsaturated zone and potentially to the saturated zone. And we have these terms here. So the Hortonian runoff, that's in the land surface, but we have the Donian surface runoff and the interflow. That's an outflow from the soil zone into streams and lakes. So when we looked at these budget components on a daily basis, just to see if inflows minus outflows equal the change in storage, we noticed that there's always a negative term, meaning that outflow is larger than the inflows. We looked closely into that. We also communicated with USGS, and we figured that there is a term that's it's odds recharge, the on-site water treatment system. So we apply odds recharge directly to the unsaturated zone, but when these budget components are reported in the CSV file, this odds recharge is added to the term. So when we look at the mass balance of the soil zone, we have a larger flow than it should be for the term, because not all that is from the soil zone. Most of it is from the soil zone, but we have this odds recharge as well. So we realized that we needed to subtract this odds recharge from that reported term in this water budget file. And when we did that, mass balance was 0. So just to explain, that's how we applied the odds recharge in the GSFlow model. So in a normal ModFlow model where we don't have the soil zone and we have the unsaturated zone like the UZF package, recharge is usually an input to the model. So recharge that goes to the unsaturated zone is an input to the model. So there is a place in the UZF file where we input the recharge to each cell in each stress period, like each month, what's the recharge in each cell in the model. So that's in a ModFlow only model, and there's a place in that in the UZF packages to do that. When ModFlow is integrated with PRMS and GSFlow platform, this input in the UZF file is read, but like it's no longer used. It's still there is still a location for it, but it's no longer used because it's overwritten by the calculated recharge from the soil zone to the unsaturated, which is an internal calculation within GSFlow. So we know that we needed to apply this odds recharge, and we found there's a new option that's only available in GSFlow. It's called Save FINF. And when we have this keyword option in the UZF file, it tells the UZF that whatever we apply here, not override it with the calculation you make. Just add it to whatever recharge from the soil zone to the unsaturated zone. So we use this save FINF option, and we had this auth recharge input to the UZF package. And the model now is calculating the recharge normally from the soil zone to the unsaturated zone, and also calculating recharge directly to the unsaturated zone. But the problem is when it's reported in the mass balance tables, it's all reported under just one component here, and it needs to be separated to get a correct mass balance calculation. Any questions? So I'm going to go through a series of these, and then I'm going to go on hands-on, like look at the CSV file again, and look at the spreadsheet, and look at some figures that we plotted using these components here. But just get the conceptual, what these components are, and how we use them to calculate, for example, the auth recharge. So this is if we focus on the soil zone, and by doing that, we can back calculate the auth recharge. So because if we don't have that, we'll have a negative mass balance error. So we can equate that negative mass balance error to the auth recharge. So now I have the auth recharge already calculated from looking at the mass balance for the soil zone. And now I'm gonna look at the entire basin. So that's my control volume now. And these are the components, the inflows and outflows, and a change in storage if I want to calculate, or if I want to look at the water budget for the entire basin. So these now are internal flows. It's not part of the equation. So these were, when I looked at the soil zone, that was an outflow and that was an inflow. But now when I look at the entire basin, I look at all of this, change in storage. Again, these are also kind of internal flows to the basin. So it's not inflows or outflows or a change in storage.
And Farag, just to clarify, I think when we're saying basin here, we really mean like the entire watershed or a sub-watershed, not
right.
not a groundwater basin.
Right. Yeah, that's how it's like configured in the USGS budget diagram. So they have soil zone, they have basin, they have HRUs. But you're correct. Thanks, Greg. So the basin means the entire watershed.
Or it could be, if you're looking at a particular area, it could be a sub-watershed that you define.
Not with these files, because these files, okay, the CSV file is the water budget for the entire watershed. It's not a cell by cell.
Got it. Thank you.
So Greg or Farag, this is Trey again. Is it possible to break it out using zone budget or something for individual groundwater basins?
We will discuss that after. Yeah. Like it's not as straightforward, but we have to look at multiple files to do that.
I think the answer is yes, it's possible. We're going to look into it, but I don't know if we're sure about using zone budget, but we've developed some methodologies to do that I think Farag's going to go over. Is that right, Farag?
That's correct. Thanks, Greg.
Sure. Thank you. Good question.
Any other questions? So these are the inflows and outflows for the entire watershed. If we want to look at the entire watershed, not just the soil zone or the unsaturated zone, or just look at the entire watershed. And again, when we calculated these inflows and outflows and change in storage, we ended up with a negative mass balance. And how we also investigated that. And what we found is there's also a mass balance component that's missing in that file. It's used correctly in the model, used correctly in the equation, but it's just not reported in that CSV file. And that's the irrigation water. So what we have in GSFlow is a file called a water transfer file, and that has flows or volumes that's applied to irrigated fields. And it's basically, we calculated that using pumping from irrigation wells, agricultural wells, and also SFR, like divergence, irrigation divergence. And we added that all together to get the volume and applied this volume to irrigated fields. So that volume is not going to be lost from the model entirely. It's going to be applied. Most of it is going to be lost as ET, but we let the model calculate that. But we'll apply that to irrigated fields, and it's going to be part of this land process here. So some of it is going to infiltrate to soil, and most of it is going to be lost through CAB-ET, but that's an additional water that's applied to the model, and it needs to be reported in the calculation of the water budget for the entire watershed. So when we calculated the water budget for the entire watershed, as I mentioned, we ended up with a negative mass balance. And when we assume that the mass balance error is 0, that's the only unknown now. And that's how we calculated the irrigation water. So irrigation is simulated in a Ventura River watershed model using the water transfer module. It's a new module. It's not in the original GSFlow documentation. It's a separate documentation. I think it was published in 2017. So that's a new module, was not available in the original GSFlow, and it can allow moving water from one location to another. And we back calculated this irrigation water by looking at the basin budget or the watershed budget. We can also look at HRUs, and HRUs is basically the soil zone plus the land surface processes. And that's HRU throughout the entire model, except for the lake HRUs, just the land HRUs. So we already calculated the odds recharge by looking at the soil zone. We calculated the irrigation water by looking at the entire watershed. Now we're gonna look at HRUs and make sure that everything like we have a good mass balance here. There's no other missing water components at this point. So when we did that, these are the inflows and outflows from the HRUs. This component, we need to subtract the odds recharge from it, because that should be only flow from the soil zone to the unsaturated zone. So we need to subtract this. We have the precipitation Q, that's the precipitation into the entire model domain, like land HRUs and lake HRUs. But if we're gonna look at the mass balance for like land HRUs only, we need to somehow calculate the precipitation in the lake and subtract that from that reported volume here. So when we do that, like subtract the lake precipitation from here, subtract the odds recharge from here, get the irrigation water that we get it from looking at the basin budget and all these flows and outflows and change in storage, we should have a mass balance close to 0. So that's going to be a good check for us. If it's going to be close to 0, then we have that means that the model is converging correctly. Because when we looked at the mass balance for the soil and for the basin, we ended up with some large negative mass balance error, but it's not because there's a problem in the model, it's just because not all the flows were reported. And when we account for these missing budget components, that's going to be the check on the error in the model. So we'll need to calculate the lake precipitation. There are different ways to do that. When we look at the examples shortly, I'll see that I calculated that using the gauge file that Jay talked about earlier this morning. Any questions so far? Right, great. So this file, the GSFlow Summary.csv file, it has a daily water budget for these 38 budget components. We also can back calculate 2 additional components, the irrigation water and the outreach charge. So now we can have a daily mass balance for the entire model. But we also find the list file, that's a standard output file from MSFlow, is also available, or like also useful for developing water budget for the entire model domain. Because, for example, here, the lake exchange to set Q or stream exchange to set Q, that's just one number is going to be reported. So it's going to be either a positive number if flows going from streams to saturated zone, or a negative number if it's the other way. But it just like we know that some streams are gaining and some streams are losing, but this number is going to be just the net on the day in all the stream segments. But it could be an interest to know the magnitude of these 2 numbers, like how much inflows and how much outflows, not just the net. Also, this here, that's the net boundary flow to set Q. That's just one number. So that's all the boundary flows that goes into the MSFlow. And we have 2 types of boundary there. We have a general head boundary at the upper Ojai. That's an inflow boundary. And we have a constant head boundary at lower Ventura. That's mostly an outflow boundary because water flows through to the ocean. And what's reported here in that GSFlow summary file, it just like outflow minus inflow, basically, just one number. But we can also be interested in knowing what is the inflow and what is the outflow, not just the net between them. And that's where the list file is useful. So the list file, each stress period, we have a table like this. So that's stress period 5 times step 28. So that's February 28 of 1994. So we have at the end of each month, we have a table like this. And we have this right column here. That's the rates in cubic feet per day for that specific day. And then on the left-hand side, we have the cumulative volumes for each of these components since the beginning of the model to that day. So that's how much storage since the beginning of the model, or let me look at the, for example, ET here. That's how much ET volume, that's in cubic feet, not cubic feet per day. That's the volume in cubic feet in all 5 months. And since October 1, 1993 through February 28, 1994. If I look at the table at the next stress period, I will have a different cumulative volume here, which is going to be throughout the all 6 months. So I can run a script or a tool that goes into this list file and feeds in the numbers there. And each stress period, it will subtract the cumulative volume from the stress period before it. And that's going to be the volume on that month only. So that's a good tool also to look at, because now we can separate between stream leakage in and stream leakage out this way. Although in the CSV file of the GSFlow summary, these numbers were just the net numbers, not the in and out. Also, we can have different values for the constant head and the general head boundary. That's the head depend bounds. And I showed in the previous slide that this is also reported as just one number in the GSFlow summary file. So looking at these two files together, that's going to be a good way to build the budget for the entire model. And next, I'm going to go in live demo just to show how to do that. This is explaining.
Maybe just quickly talk about, I can mention that it's important to understand that the right-hand side of this diagram, the rates for this time step, is just the rate on that specific day.
That's correct.
And you can't assume that that is a constant rate throughout the entire month. So it's a fairly common error to make in these kind of water budget analyses, to assume that that rate can be applied to every day within the month. And particularly in GSFlow with these daily time steps, that's going to cause error. So that's just another reason why we focus on the cumulative volumes that are calculated every time step and reported every stress period in the list file.
Thanks, Greg. Like we noticed in ModFlow only models, even if stresses are applied uniformly throughout the whole stress period, because we have water that goes up and down within the stress period, these might not be the right, like assuming that these numbers are uniform throughout the month and multiplying by the number of days a month to get the volume there can introduce some kind of problems. But this problem is even more pronounced in GSFlow because we are dealing with varying flows on a daily basis. Thank you, Greg.
Yeah, and sure. And I believe the zone budget tool, for example, is looking at the rates. So
unless like flows are printed every day, like if we select to print, but which is going to be a huge file. So if there's an option in ModFlow to print a file called cell-to-cell flow file or CBB file, and the zone budget assumes that the times between the reported or the reported times in CB in that file flows are constant. So
yeah, we think that if we were to develop a daily cell-by-cell flow file for this model, it would be about 1 terabyte large.
I think I calculated. I never attempted to do that, but I think I calculated that in the beginning. Yes. So that's why we're trying to look at ways to look at volumes over a period of time, not just rates, and assume these rates are constant throughout a certain period.
Thank you.
Any questions? So I'm gonna minimize that. And I have a folder here called water budget. And these are the diagrams we're just looking at. This is published by USGS, and that's for all budget components. This is basin budget, which is the budget components for the entire model. And this is the HRU budget. So we went through all of this, and this is explanation of these budget components. So we should have 58 of these here. So this is a spreadsheet. And before I go to the spreadsheet, I mentioned that there is a tool that we developed. It's called read results.exe, and that tool, it basically goes through the list file. So this list file is, for example, 64 megs, and I can open that in text that, not text that, TextPad, and so that these are the tables I was looking at. So that's the cumulative volume in stress period 1. That's in stress period 2. And if I move down, I just a lot of number there, but what I'm interested in is these tables. And I can look at that. This is the cumulative volume in stress period 3 for storage. And this is the cumulative volume in stress period 4. And if I subtract these two numbers, that's going to be the volume in storage in that stress period only. So we developed this tool here. It's called read results.exe. And basically what this tool does is it goes through the text file, looks at these kind of tables, and calculates the mass balance component for each at each stress period. And then it prints the results here on that summary list file. So look at the summary list file. It's last time was updated yesterday at 5:28 p.m. If I had the read results.exe file here, just go through the list file, and it created the summary list file annual. So just date it now. And if I open that, it just gives me the information. So that's the water year, pumping. So that's the recharge through the SFR, from SFR to groundwater, and that's gaining streams. So reach flows from groundwater to SFR. That's the seepage from lakes to groundwater, and that's the opposite. It flows from groundwater to lakes. And we can, that's the inflow from Upper Ojai, that's the outflow through the ocean. That's the recharge from the soil zone to the unsaturated zone. That's the surface leakage when the water table is high and it discharges back into the soil zone. And that's the ET and the difference in the storage. So all of these were calculated from the list file. And numbers here are in acre feet per year, because I just having every water year. So this tool is also available. So, but I'm opening now this spreadsheet. It's called Groundwater GSFlow Summary. And you can see that there are 4 tabs there that are colored. And this is the tabs where I want to copy and paste some budget flow components into here. So the first tab is the GSFlow Summary. And so we need to copy this file here, the GSFlow Summary file. So I'm gonna here. So this file is created by GSFlow as the model is running. So each day it will create the 38 budget component here at this file. So I can copy that after the model is completed. I can copy that and paste it here. Then the list file, this is the file that I was just created using this tool. It's here, I just created now. So I can copy that. Sit here and paste it here. So just paste it in just this column. I'm gonna have text to column and so now it's pasted here, and that the mass balance error in the ModFlow only, because that's the list file. So that's only a ModFlow portion of the model. I'm gonna copy these later, but these are the two files that I wanted to look at. And then I'm gonna, for example, look at the saturated zone. And this is just built-in formula there. It gets the information from either the GSFlow Summary file or from the list file. So I can have what's the groundwater recharge every year, what is the SFR leakage, seepage and ET and surface leakage and the mass balance error. And we use this information to plot this diagram. That's the inflows and outflows. And Greg went through this on day one of training, but this was created using these two files here, the GSFlow Summary and the list file. We can look at the soil zone, and we have the infiltration, that's infill to soil Q, CAP ETQ, which is the evapotranspiration from the soil zone. And we have all this information. And remember, in the water budget for the soil zone, we had this missing component, the R3 charge. So we back calculated this R3 charge by equating the mass balance error to 0. And we just back calculated this R3 chart this way. You can look at these formulas, and again, it's getting the numbers either from this tab or that tab here. In the presentation, also, we looked at the basin or the entire watershed. The basin here in the GSFlow terminology means the entire model or the entire watershed, not just the groundwater basin. But we can look at the basin here. The R3 charge, we already calculated it from looking at the mass balance for the soil. So we're copying this number here, and we're getting all other budget component for the mass for the basin or the entire watershed, and just a missing component, which is the irrigation water, and we back calculated that by equating the mass balance error to 0. So a good check would be looking at the HRU, which is the soil plus the land processes of each HRU, of each land HRU, not the lake HRUs. And so this number, we already calculated the R3 charge, we already calculated it from the mass balance of the soil. This we already calculated from the mass balance of the basin. And we also need to calculate the lake precipitation, because this number here, it's a precipitation to both lake and land HRUs. And we calculated this by just using the gauge Matilaha and gauge Casitas. So this is a text file called, its output in the model. It has daily information for gauge Matilaha, like what is the stage, what's the volume, what is the change in volume, what's the precipitation, what's the evaporation, all in feet per day. So it has all daily information from throughout the simulation, and the same for Casitas. And we use this field here, the precipitation in both Matilha and Casitas Lake, to calculate the lake precipitation. So that's basically the sum of these two, like Matilha and Casitas. And then we subtracted that number from here, and we calculated the mass balance. And that's the actual mass balance error we have in the model in acre feet. So in the soil and the basin, we equated the mass balance error to 0. That's an approximation, but we wanted to see how bad this approximation is. It's not that bad, because the actual mass balance error is not that big anyway. Any questions so far? Okay, so I'm gonna go. Trevor had interest, and I'm sure other people might have interest in looking at distribution of these budget components, especially. So we looked at the total budget components for the entire watershed, or portion of the water, like the soil zone in the entire watershed, or the saturated zone in the entire watershed. But these two files, the list file and the GSFlow Summary CSV file, will not tell us what is the spatial distribution of these volumes are. And we need to look at other files to do so. And that's what I'm gonna discuss next, if no one has questions so far. Okay. Should I proceed?
Yeah, I think if there's
okay.
no questions.
I cannot look at the chat window.
Yeah, there's no questions in the chat there.
Okay. We looked at the developing water budget for the entire watershed. And now we're gonna look at other MSFlow and PRINCE output, which are useful for developing water budget for each cell in the model, not just the entire watershed, or a certain zone. So there are other MSFlow and PRINCE output that can be used to estimate water balance. One of them is UZF net flux option. So that's an option in the UZF package. And when we do that, like, remember we talked about the CBB file and how it represents flow at a certain day. Like, it can be useful for reporting budget for that day. But if we want, like, if want to do an assumption and assume that day is representative over the entire stress period, the entire month, that might not be a good approximation for most of the boundaries we're dealing with, especially in GSFlow, where we have changing daily flows, changing daily, like recharge and percolation from streams. So the good thing about this net flux option in UZF, it's calculating a volume, a cumulative volume over a certain period of time, not just rates. So we use that option, which will allow us to calculate a volume over a period, not rates. Also, some other PRINCE output files like recharge groundwater rejected, GW2SM, that's groundwater to soil zone, so that's the surface leakage. So flow discharging back from groundwater into the soil if water table is high. And ACT, ET, groundwater, these are the exact names as in the Prince manual, and that's the ET from groundwater. So in combination of the UZF net flux and these 4 PREMS output files, we can have a distribution of many of the water budget components. So what the net flux option in UZF does, it prints the sum of total recharge and total discharge in each cell. And total recharge is recharge from soil to groundwater, plus out recharge, plus stream flow percolation to groundwater, plus lake seepage to groundwater. So all of this is reported as just one number, but it's different spatially from one cell to another. Net flux discharge from MSFlow cell, that's the summation of 4 budget components as well. That's the ET from groundwater, the surface leakage, gaining streams like flow from groundwater to stream flow routing package, and also groundwater to lakes. So if water moves from groundwater to lakes. Again, this is just one number as the sum of all these components, but this number changes from one cell to another. So this is one piece of information we have, and we are going to use the other PREMS file trying to separate these different components. So the odds recharge, that's an input we have. So we know that we have like how many odds in each cell, and we assume a certain flow from each odds, and we're going to discuss that on the 3rd day. But that's an input to the model. So we know the spatial distribution that we input to the model for odds recharge, the on-site water treatment system. So that's one component here. These are 2 files, the recharge monthly.csv and groundwater rejected monthly.csv. These are 2 files that are created by PREMS, and we defined, like we listed these 2 files in the control file of PREMS. So we asked the model to print these 2 budget components on a monthly basis. And PREMS usually, not usually, PREMS prints the volumes over a certain period of time. So that's what we are after. So the recharge monthly.csv is basically what is the recharge in each cell that's happened over a certain cell. But that's a potential recharge, not the actual recharge. So that's the potential flow from the soil to the unsaturated zone. Some of this potential flow is going to be rejected, either because water table is high and cannot accept any more water, or the unsaturated zone has a low vertical hydraulic conductivity, lower than the infiltration rate. And that rejected volume is reported in that file, the groundwater rejected. So if we subtract the groundwater rejected from the recharge monthly, we end up with the actual recharge from soil to groundwater. And that's another component that's listed in the net flux option on UZF. So now, if a cell is not a lake cell or not an SFR cell, so we can calculate these 2 components here from like this component we calculated from prems output. This component we just calculated. We know what we input in the model, and we sum these two components, and we can double check what net flux printed as a net flux recharge for that cell. Should be the sum of these two numbers. If the cell is an SFR cell, you'll probably see that net flux is higher than these two numbers, and that remainder is going to be the SFR to groundwater. So that's how we calculate SFR to groundwater in each SFR cell. If it's a lake cell, then the remainder is going to be remainder between net flux and the sum of these two components are going to be applied to the lake to groundwater recharge. So by getting the net flux, calculating this from input, calculating this from prems output, we can have monthly spatial recharge to each cell, either recharge from soil or leakage from SFR cell or lake if the cell is SFR or a lake. So the same also can be done for net flux discharge. So the net flux discharge is the sum of ET plus surface leakage plus these two terms here. And we have a file, a prems output called ACT-ET groundwater, which is basically what the ET in each month in each model cell. And we have this as the surface leakage. So again, if the cell is not an SFR cell, not a lake cell, then we calculate these two terms from prems output, and we can compare it with the net flux discharge from FM from MSFlow cell. Should be exactly the same. This number reported here and the sum of these two numbers. If the cell is an SFR cell, so we first can calculate these two from prems output, and we have the net flux discharge, the remainder between the net flux discharge and the sum of these two numbers are going to be applied to either an SFR or a lake, depending on whether the cell is an SFR or a cell or a lake cell.
Hey, Frog.
Yeah.
We got a question in chat from Randall Hansen. Do you mind if I read it out loud?
Yes, please.
Okay. What percentage of total precipitation is Hortonian runoff for each year?
I can go back to the spreadsheet we have. Should I do that now? I just have a couple slides to finish.
Okay, yeah, let's go back, I guess, when you finish those slides.
Okay. So by outputting the net flux and the recharge and these four prems output, we can calculate all of these components as a spatial distribution to each cell, and that's going to be a volume over a period of time, not rates and multiplied by the number of days. So we calculated a lot of recharge components, a lot of discharge components. We calculated the boundary flows. Pumping, we can calculate it. Well, one of the output file is test.bym by node well. So it has daily simulated pumping for each well. So we assign the pumping for each well for the entire month, but depending on the water level within the month, some of this pumping might not be applied fully for that well at this stress period, and this information is going to be located in this BYN file, which lists this simulated pumping, the actual simulated pumping in each well for each day. So cell to cell flows file, we try to avoid that as much as we can, but there are other budget components that we only can calculate it from the cell to cell flow files, like flows from one cell to adjacent cells. So we can calculate these flows from CBB file, and we assume that this flow is not going to be changing much during the month. So normally the changes are going to be most in third type boundary conditions like rivers, streams, drains. These are that we want to avoid the CBB file in the calculations. So if we do all of this, we will know all budget components except for change in storage, and we can equate the change in storage to zero, like not equate the change in storage, like if say inflows, total inflows minus total outflows is the change in storage, and that's the only unknown component now is the change in storage. So we can calculate that to each cell. So to summarize, we can do interpretation to multiple ModFlow and Prince output files, and that will allow us to calculate a complete mass balance in each model cell, and we can have that for a certain zone. If we calculate it for each cell, we can delineate zones and calculate the mass balance for the zone. So this is my last slide. I'm gonna go back to the spreadsheet I have, a look at Ren's question. Any like, while I do that, of course, you can ask questions. So question was, this is the precipitation that's in acre feet and the Hortonian surface runoff. That should be here. So I'm gonna add it here. So this is the precipitation that falls directly to the lakes. I'm going to calculate the precipitation that's on the land, the HRUs, and that's what we are after here. And that's the Hortonian surface runoff, 2 streams and 2 lakes. So this is the, like, not this, that's the outflow. So that's basically the surface runoff to the streams. So, but of course, there is like Hortonian surface runoff from one cell to another. That's not reported here. And that's all the surface runoff. So the Donian surface runoff, the interflows, and all the components here.
Thank you, Farag. Does that answer your question, Randall?
I don't see a percentage on there, but
okay. So
that's fine. That's fine. I calculated it the same way.
All right.
Just surprised how little it is.
Yeah, so it's ranging between 5% to 40%, 48%. this is usually like the wait years, 1995, 1998, 2005 and 6, 2005 was a wait year as well. Any other questions? So I can, if there's no other question, I can show this file in unimpaired scenario. It's much easier because in unimpaired scenario, we don't have lakes and we don't have outreach charge, we don't have irrigation. So just a straightforward there. And so we don't need to do any back calculations or anything like that. So the unimpaired scenario, if I look at the water budget, so these are the two files that I need to copy, the GSFlow Summary.csv and the list file. And the list file is copied by first running this tool here, the read results.exe, and it's going to create a text file here that we copy here. But there's no gauges at the lakes because there are no lakes in the unimpaired scenario. And then that's going to be the mass balance, and always have a mass balance here. That's a very small number. In the soil, just to have consistency with the file format and everything, I still have the outreach charge, but I have all these numbers are zeros. And this is an actual mass balance error now. It's not, we're not assuming it to be zero to back calculate this value. We're already having zeros in here, and these are the actual mass balance error for the soil. For the basins, also, I'm having these as zero. And this is the mass balance error here for the basin. So again, I'm not assuming that to be zero and back calculating the irrigation water, because there is no irrigation water in the unimpaired scenario. So that's forward calculated, not back, not back calculated. For the HRUs, also, I don't have any any precipitation on the lakes. This is all zeros, and this is just the mass balance error for the HRU. Of course, there is no, like, these terms are zero there. In the basin, we have no wells, so pumping is zero. Lake ET is zero because we don't have any lakes. So these numbers there were numbers there in the calibration run. And we calculated the total precipitation, the total irrigation, and everything. The total ET is ET from all these terms here, like canopy ET, snow ET, impervious ET. Of course, most of it is ET, evapotranspiration from soil. We have a groundwater ET from the saturated zone, the shallow groundwater. And so we calculated the total ET in here. And that's also another plot that Greg presented in day one. So that's inflows and outflows for the entire watershed. And these numbers are calculated from that file here. Any questions?
We are nearing we are nearing 3. So if you have questions for today, please don't be afraid to speak up.
Yeah, and there's a lot to take in there, especially you haven't worked too much with these types of models before. But feel free to ask questions.
Kevin, just a couple of questions, if you can, it's pretty handy.
Yeah, I can try. What's up?
Yeah, it's basically in regards to the lake. I know yesterday they were talking about the original capacity was 254,000 acre feet in 2017. It was rated at 237,000 acre feet. Has anybody looked at, and also you have during the years that you're running your simulation, there was also some spills from the lake. Have those been computed in to show the decrease in size of the lake in the appropriate years based on the barometric survey between the original construction and the date of 2017 to figure out the differences in what the flow would be down the river, and also when you have spills from the lake, how's that computed?
Right, I can try and answer that first, but I will defer to Al to help fill in the gaps. So I think we fixed the capacity of the lake for the modeling period. And I think
Correct.
it's fixed at that 2017 volume.
Yeah, correct.
So I don't, does that answer? Okay.
Yeah, we don't really know when, you know, most of that sediment arrived. It was kind of a linear buildup over time, or there was some, I'm sure it's more in wet years than dry years. So I'm not sure if we'd even have information of what the capacity was in the early 90s. But the model is kind of limited to a fixed capacity. I think it would mostly be kind of, I don't think it would greatly affect the results because it's just going to, you know, you'd have a different volume of water in the lake, but it's not like we're ever drying up the lake in these scenarios. So if there's more or less volume, it doesn't matter too much. The model does predict spills, I think. So in 98, I'd have to check back on that when the lake fills up and some of those.
Yeah, there were about 3 or 4 years where there were actual spills.
It was 05 as well.
A couple in the 90s and a couple in the early 2000s.
I'd have to check back on that.
Okay. I will add that we got quite a bit of operations data from Casitas Municipal Water District regarding inflows and outflows from the lake. And so I'd expect that if we have data on the spills, it would be in what they provided us, and then, you know, we could compare that against what the model simulated. So does that answer your question?
Yes, it does. Thank you.
Yeah, you're welcome. Anyone else? Okay, well, let's keep going. Thank you. Al, what's the where are we going next, or are we wrapping up?
I think if there's any more questions, we can take them. But that's all we had today. We can touch base. Sorry, I've lost the screen. We can touch base. You know, a brief overview of what to expect on Friday. So on Friday, so today we're really looking at, you know, how to look at the model results, how to process the surface water at different locations, how to pull out groundwater elevations out of different locations, how to do all these kind of mass budgets, which are very useful and common. And we thought we'd start there because that's, you know, we've already got the calibration and the unimpaired flow scenario. So those, you know, there's a lot of information in there. We only presented so much of it in the calibration report, but you can really get in there and create any kind of outputs that you like, with hopefully what we've shown you today. The focus on Friday is going to switch to making modifications to the model. You know, we've kind of mentioned on Monday and today, you know, the model's fairly complex. It's this HRU based or distributed model for the hydrology part, plus a full groundwater model. We've developed some tools to hopefully help people deal with the input files. The input files for these models are typically large text files, which can be difficult to work with. So on Friday, we're going to present tools where you can, I guess to summarize in a nutshell, work with some simpler text files and then run these tools to create the more complex model input files. So you can change things like hydraulic conductivity of different zones of the groundwater model, store activities, different you know, storage and rate parameters for the surface water or the PRIMS part of the model. And that's what we'll go over on Friday.
Al, is there anything that you would tell people to have prepared from the zip files for Friday?
I think it's all in there. There's no installation needed, no groundwater vistas. There are a text editor, which I should have pointed out. People should have a text editor. Their favorite ones, I think, Parag used TextPad, Jay used Sublime. Windows has Notepad, which is maybe not the best one. And then there's executables in there. It's typically just a kind of double click and they'll run. GIS, I guess Jay will be opening up some files in GIS if you want to have a GIS ready to go. That might be helpful, but I wouldn't say it's essential.
I think we have time for 1 or 2 questions. I did just get a message that this division water rights sim account needs to be used for another meeting at 3 o'clock. But if anyone else has maybe 1 or 2 more questions, we could stay until 2:55, perhaps at the latest.
Kevin, off topic, a couple of things. There were 2 groups that were actually playing at the first concert. It was Nitty Gritty Dirt Band and the Stone Ponies, and I sent you an email regarding that.
Thank you. I need some new music to listen to. I'll have to. Well, I don't know that we'll need to do introduction.
Wow. Is there anyone else besides me that knows who the Stone Ponies are and the person that referenced the band on the phone? That's pretty impressive.
Yeah, no, I actually used to go see the Stone Ponies in Tucson. They played at the Stumble Inn with Linda Ronstadt.
Of course they did. Yeah.
Parents their family still, some of the family members still play in Tucson, actually.
Amazing, amazing.
Randy, you beat me to it.
So one thing just I forgot to mention, I said I'm gonna revisit this and I forgot to do so. As this is the batch file to run the GSFlow, and it has the executable file and the control file. And these are just to run the tools that we discussed today. So these tools are gonna run automatically after GSFlow is run. So basically, we're running read results.exe, which is the executable file that summarize all the budget component in the list file. And that's the one that Jay discussed is the SWRCB.exe, which is formatting the SWR file in a different way to be looked at. So these two components, like these two executable, can be run individually, but we added them to this batch file, so they always run after the GSFlow executable is completed.
Thank you, Farag. Okay, I'm going to issue a last call for questions. All right. Well, thank you everyone for attending. We are going to save this recording and post it on YouTube. I'm going to stop the recording now. So questions going, gone. Okay. Stop recording.